Bonjour à toutes et à tous. Thank you for being here this morning. We are pleased to welcome Sandra Hunter, a very special guest from US. So Sandra Hunter is a professor in Neurophysiology at the Department of Exercise Science at Marquette University, Milwaukee. So I first met Sandra Hunter in 2001 when she was in postdoc in University of Boulder, Colorado. And later she moved to Wisconsin, where she has been in faculty since 2003 now. So today she will sharing her expert opinion with us on sex difference in fatigability. So I ask you that you give your full attention to Sandra Hunter. Sandra.
All right, there's 3 devices here to project my voice, and I'm not sure which one to use. So thank you so much. The hospitality, the French hospitality has been fantastic. Thank you, Romu. Like he said, I met him in 2001, and when I was a postdoc in Roger Anoka's lab. But I'm actually not American. Maybe you've picked that up already, or maybe you haven't. I speak 2 languages, Australian and American. Unlike you, I really only speak English, and I applaud you for being bilingual at least, and I feel inadequate speaking in English here, but that's all I've got, so that's what you're going to get. So when you ask questions, it'll probably have to be in English or someone's going to have to interpret. All right, so this is a topic that really excites me, and it started to research this area when I was in Boulder, Colorado, about the time that Romu showed up. And it's an important area. 2001 was when I met Romu, but it's also the first review paper that appeared on sex differences in fatigability, also known as muscle fatigue. And I'm going to tell you today why it matters, because historically, a lot of the experiments that are done in exercise science, in exercise performance, and a lot of the physiology that we understand about the response to exercise is because of studies conducted on men. But there are profound sex differences in the way women and men respond to exercise. And so I want to alert you to some of those and to encourage you to include women in some of these exercise studies. And a lot of those differences occur because every cell has a sex. And as a result of that, there's potential sex differences in gene expression in every cell of the body. And that's due to non-gonadal functions directed by the sex chromosomes, but also because of gonadal effects via genomic actions of the sex hormones themselves. As a result, we can have some profound differences between men and women. And compared with women, men usually have more muscle mass and usually a larger fibre size, a larger percent area of the type 2, the fast fibres, compared with women, larger hearts, more haemoglobin, less body fat, and ultimately that can lead to differences in strength, where men are stronger than women on average and they're faster. So there's these absolute differences that we can gain insight to the true physiological sex differences by looking at world records and looking at the percent differences. So here we have the 2 world record holders of the marathon, and there's about a 10% difference there. And if you look across many of the world records, running from sprint distance right through to the marathon, and swimming and jumping that I've just highlighted a few here, you can see there's anywhere of a difference between 6% up to 16%. So on average, around about a 10, 11, 12% difference in exercise performance between men and women. And these world records give us insight, particularly when motivation and training don't seem to differ between the sexes, at least anymore. Up until about 30 years ago, that was not the case. I also want to suggest to you that fatigability of limb muscles can really define some of these performances and the limits of performance in both men and women. So when we talk about performance fatigability, we're talking about the decline in an objective measure of motor performance over time. It's acute, it's reversible, it occurs during maximal and submaximal tasks. And some examples include a decline in running or walking speed over a distance. Here's my daughter doing one of her first triathlons. And some unknown lady here, that's not my mother. Although she looks pretty good, doesn't she? Also, reductions in cycling power, such as that occurs during a time trial or any cycling over a set distance. And also, what we often measure in the laboratory setting is a decline in force, velocity and power during single limb exercise. And sometimes we take these reductions in single limb exercise and we try and make inferences about what's going on in whole body exercise. So when we go to the laboratory setting and we can define fatigability as an acute exercise-induced reduction in the expected or the desired force output of a muscle or a muscle group. And so fatigability can occur during both maximal and submaximal exercise. And that's shown here in this force record where we've asked someone to perform isometric intermittent contraction with the elbow flexor muscle. So when this woman activated her elbow flexor muscles, and here's a force transducer here, we saw a force and we asked her to perform at 50% of her maximum for 6 seconds and then followed by 4 seconds rest. And we asked her to sustain that contraction until she couldn't sustain the task any longer. And I want you to note, however, when we measured maximal strength throughout the task, you can see that the maximal strength is declining even though she's able to successfully perform the task until a point of task failure. And so we can often quantify fatigability as a reduction in the maximal force or power or the time to failure of the submaximal task. But as Sam noted yesterday, that sometimes these are disconnected, and I think I'm going to show you some evidence as to why that occurs. Now, a really important aspect of fatigue to understand is that there are multiple mechanisms that contribute to muscle fatigue and fatigability. And while ultimately the force output occurs here at the muscle, and a lot of the fatigue does occur due to mechanisms within the muscle, that inadequate activation and inability to supply enough action potentials at an adequate rate or enough of them can really lead to decrements in force output. And it's not such a simple thing to understand or to study because there's feedback that does occur from the muscle to spinal centres and to supraspinal centres that can then affect the number of action potentials propagating to the muscle. Another really important aspect to understand, and I think this is really key, is that fatigability is very specific to the demands of the task. It's task specific. And what that really means is that varying the task requirements, whether it be a maximal contraction or a submaximal contraction, dynamic, isometric, will stress different sites along this neuromuscular system, influencing the mechanism and the magnitude of fatigability. And I'm going to show you evidence of that today. And also how the sex of the person can also influence fatigability. So it really complicates it. And any sex-related differences along this neuromuscular system, whether they occur within the muscle or within supraspinal centres or in activation at the spinal centres themselves, will result in a different mechanism and magnitude of fatigability for men and women and a different rate of fatigue. And so while I've been talking about how fatigability can really define the limits of performance of both men and women, I also want you to alert that this is actually a positive thing. We can use fatigue because it actually underpins and leads to neuromuscular overload, which is necessary for effective rehabilitation and training. And that's a really important aspect that we often miss. And that's important because often when we prescribe exercise, particularly in rehab, rehabilitation and training, we prescribe exercise at a relative intensity, whether it be 80%, 50%. And so a really important question, I think, to ask is, are there sex differences in fatigability? And does this have implications for men and women during rehabilitation from injury or during training? And so just as a quick outline of today, what I'm going to talk about is what we know and what we don't know. I'm just going to try and summarise a broad, a lot of literature in, and this will be a lot of the talk today. Then I'm going to end with, and I love this part of the talk, where I'm going to try and convince you that the number of men and women we include in our studies can really affect our understanding of what we know about fatigability and exercise performance in the population in general, that's being men and women. And then I'm going to provide insight into new opportunities as we move forward. So one of the first studies we did in this area was when I was in Roger Anoka's lab, and Romeo just showed up at the lab. And I don't know if you recognise this human specimen here, but he happens to be just in the front row, the second row here. This is about 14 years ago. I tried to get your head in, but I couldn't. I'd cut that out. So we asked subjects to perform a contraction at 20% of their maximum with the elbow flexor muscles and sustain the contraction for as long as they possibly could. We had very strict criteria that was across the board. And what we found is the time to task failure, or sometimes called the endurance time, was very different between the men and the women. And the women were able to sustain the contraction over twice as long compared with the men. Now, the men were twice as strong as the women, and I'm going to tell you about that in a minute as to why that has implications to one of the mechanisms. But this was one of the first studies we did that really alerted me to the fact that there's these huge sex differences when we measure exercise performance relative to maximum. And what I've done here is summarise all the studies to date that I can get my hands on, and that's over 55 studies, where each data point here represents the sex difference or the difference between a group of men and a group of women for one study. And so on the y-axis here we have the sex difference in fatigability as a function of the force that they were contracting the muscle at, and these are sustained or intermittent isometric contractions, and across a bunch of different muscle groups here. And you can see any data point above the line here indicates that the women were more fatigue resistant for that study, for that muscle group, and for that force output. So most of the data points here are above the line, indicating that on average there's overwhelming evidence that women are usually less fatigable than men for these isometric contractions. But just if you look more carefully, you can see that it doesn't occur for every muscle, and that if you take the ankle dorsiflexor muscles, for instance, they have much less of a sex difference than, say, the elbow flexor muscles here in the blue. And there's also a bit of a regression here that this sex difference seems to become less towards maximum contractions. And so this graph here shows that women are more fatigue resistant than men, but also suggests that the sex difference is very specific to the task demands. And so rather than ask the question that I started off back in 2001, which was, what is the mechanism for the sex difference in fatigability, I quickly changed to what's the magnitude and mechanism of the sex difference in fatigability when the task is varied. And so I put together a model, and this really developed. It actually started with this. And then I put together this model, which I keep developing, and it's very complex. It's actually sort of not that complex when you start with just this. But here are the neural mechanisms and the possible neural mechanisms as to why women are less fatigable. This cascade of events here is really only relevant during sustained contractions. That because men, we found that when men are stronger than women, that during sustained contractions, even though they're sustaining contractions, say, at 20% of the maximum, they've probably got a greater occlusion, greater mechanical compression onto the feet arteries, less muscle perfusion, and therefore a greater and more rapid buildup of metabolites that then leads to fatigue. And so they fatigue more rapidly than women, which can also then affect supraspinal fatigue and spinal fatigue and activation of the motor neurons via these group 3 and group 4 afferents. And here on this side we have more the skeletal muscle metabolism, which can really differ between men and women. One of the main points that I want to make is that the strength of the contributing mechanism here will really alter the sex difference, and it will be really altered by the details of the task. So if you have a maximal sustained contraction, there may or may not be sex differences, but that may differ to the mechanism that occurs during dynamic tasks. And so first I'm going to talk about isometric, maximal tasks, then go briefly on to submaximal and then dynamic. So one of the first questions we had in this area was, does neural drive differ between men and women? So really, what's the relevance of, is there any sex differences within supraspinal mechanisms or within the spinal cord itself that leads to differences that can explain this fatigability, this sex difference in fatigability? And one of the classic measures of voluntary activation and the ability to drive the muscle is that of the interpolated twitch or variations, where we interpolate a stimulus while someone's performing a maximal voluntary contraction. So here we've got force on the y-axis as a function of time, and these arrows indicate when we delivered a stimulus to the muscle. And you can see that during this contraction there's no extra stimulus or no extra force when the stimulus applied. Now this would indicate that voluntary activation is maximal, very close to maximal, because there's no stimulated force elicited during the contraction. However, during submaximal activation, you can see that there's an increase in the force output here when the stimulus is applied. And that would indicate that the person's not able to drive their muscle adequately. So if we see this sort of event occur after a fatiguing contraction or during it, this indicates there's some sort of fatigue within the central nervous system, often known as central fatigue. So we can stimulate here at the muscle. We can also stimulate at the cortex. And we can express this interpolated twitch force as a ratio of what the twitch force at rest, and we can get voluntary activation as a %. We can also just look at the magnitude of this twitch force itself. So we're really interested in understanding the supraspinal fatigue and whether that contributes to sex differences in fatigability. And so supraspinal fatigue can be really quantified by stimulating at the motor cortex instead of the muscle here. And this will tell us fatigue produced by failure to generate output from the motor cortex. And so this was one of the first studies I did. I went back to Simon Gandivia's lab in Australia to learn how to do this transcranial magnetic stimulation. This is one of the first studies we published. And this was the setup here where we were testing the elbow flexor muscles, and we're asking a group of young men and young women to sustain a maximal contraction for 22 seconds, and we asked them to do 6 of them. It was a brutal test, and there was a large failure of force, and we stimulated the cortex at the beginning and the end of each of those 22-second maximal contractions. And this here, this inset here, this represents the force output of the interpolated twitch at the beginning of this contraction. And this, you can see there's a growth in the this interpolated twitch here, and that would indicate that there's supraspinal fatigue occurring, and that's an inset of this here. So what did we find? Well, first we found that women were less fatigable than men, that men their maximal voluntary contraction by the end declined by 65% and the women by 52%. And so the question was, what was explaining that sex difference? Well, we found what was not explaining it was supraspinal fatigue. Certainly supraspinal fatigue occurred for both sexes, but it didn't occur differently. So this here is voluntary activation, representing supraspinal fatigue, or the reduction is the supraspinal fatigue. This is the voluntary activation during controlled contractions before the fatiguing task. This is at the beginning of the fatiguing task and also at the end. And even though both men and women, the men in blue, the women in orange, you can see that they decline similarly throughout the task. And in fact, every study that we've conducted on the elbow flexor muscles, we found no sex difference in the magnitude of central fatigue that occurs either after submaximal tasks and maximal tasks. And that's represented here. This represents just 3 of our studies. So on the y-axis here is voluntary activation and the reduction in voluntary activation. So an increase means that central fatigue was occurring. And you can see this is the men, this is the women, this is when we stimulated the muscle. This represents just 1 study. This represents 2 studies when we're stimulating at the cortex. And there's no sex difference here that we could that could explain the sex difference in fatigability. However, that's not the case always for every muscle group. And in fact, there have been some other studies by other groups shown here on the knee extensors and the ankle dorsiflexors, where they stimulated the muscle, and they found and this was Peter Martin in 2007, and this study was by Russ and Kent Braun in 2003, and they found that the sex difference in fatigability that they saw during these maximal contractions with these lower limb muscles was explained most exclusively by the fatigue within the central nervous system. So I was really intrigued by that. And so we went and did our own study, which is only just in revision now. We took a while to get this out. You know how it goes sometimes. And so what we did is we asked a group of men and a group of women to perform a maximal contraction for 60 seconds. And so both the men and the women had probably occlusion in both their muscles. And then we looked at recovery as well. And this is what we found. This is the reduction. This is the fatigue data. This is the reduction in the maximal voluntary contraction force this is as a % of their maximum, because the men were stronger than the women. And you can see that the men and women declined the same during this maximal task. This really didn't surprise me because they're both occluded. However, within 10 seconds of finishing that task and blood flow is allowed to come back into the muscle, we saw these sex differences expressed during recovery. And this here are brief contractions, maximal contractions during recovery. And here the women are recovering to a greater extent than the men. And so what's explaining this sex difference in fatigability during recovery? Well, what we found was that it was most all exclusively, just as the other studies had found, was by the superimposed twitch force, that central fatigue. Here we're measuring supraspinal fatigue because we're interested upstream of the motor cortex. The other studies had only measured at the muscle. But we can see that this decline in the superimposed twitch force, so an increase in the superimposed twitch force, indicates that there's supraspinal fatigue occurring. And so here we've got recovery, but the men had greater supraspinal fatigue than women throughout that recovery, and it parallels this change in force here. Interestingly, and to my surprise, there were no differences in fatigue when we, within the muscle as we measured by the amplitude of the twitch force, which really surprised me. But here what we have is the twitch force at baseline, and this is the men and the women, and you can see that the men are basically stronger than the women, so they're getting a greater twitch force. But when we take the twitch force during recovery relative, and you look at this axis here, there's actually no difference in the recovery, which was really interesting. And so when we take these results together with the elbow flexor muscle studies that we've done in my lab and with others, we can see that first there's a sex difference in recovery that was due to supraspinal fatigue here, and that the sex difference in supraspinal fatigue was specific to the muscle group. There's still questions as to why that occurs, but we think it's got something to do with the group 3 and group 4 feedback. And so just in summary, we found that there was no differences in the supraspinal fatigue for the elbow flexor muscles, but there was in the knee extensor muscles. So what's explaining the sex differences in the elbow flexor muscles? Well, we think it's got to do with what's going on in the periphery and the muscle itself. And one of the beauties about, that was an Australian phrase I just said then. One of the beauties, one of the really nice things about transcranial magnetic stimulation is there's this silent period in the EMG. And the person, if you've ever done it, while you're contracting, you can't help but relax when you're the subject. And during that period, we can get the relaxation of force, and which can tell us about the contractile properties of the muscle during that the state of fatigue. And so here we have the superimposed twitch force during control contractions and during and after a fatiguing contraction, at the start and end of the fatiguing contraction. And this is data from that first study that I showed you about that we did back in 2006, where we saw that there were no sex differences in voluntary activation. And what we found, so what we have here, we can measure the peak rates of relaxation of these twitch forces, and it can tell us about what's going on in the muscle in terms of the contractile properties during the fatiguing contraction. This is during, so on the y-axis here we have peak rates of relaxation, and an increase here means that there's the muscle is going faster. It's negative here because it's a negative slope, but you can see that the men had faster muscle than the women during controlled contractions, probably indicative of their muscle fibre types and them at rest. And however, they declined to a much greater degree during those 6 22-second contractions. So by the end, the men had declined by 53% and the women only by 22% by the end of this fatiguing contraction. And so that earlier study, where there were no differences in voluntary activation, were really explained by changes within the muscle and sex differences within the muscle. And we'd expect that there are sex differences in the muscle because there are sex differences in the muscle physiology. This graph here summarises 12 studies where I've graphed the type 1 fibre area taken from muscle biopsies of men in blue and women in orange for the vastus lateralis, for the biceps brachii, and for the tibialis anterior. And on average, you can see that the type 1 fibre area is greater for women than men. And in every study that is documented here, except this one here, the women had greater type 1 fibre area and probably a more fatigue-resistant, which represents a more fatigue-resistant muscle. So I was really interested, are women just less fatiguable just merely because they've got more type 1 fibre area, or are there specific differences of the muscle fibres, of the type 1 muscle fibres of men and women? And so are they fundamentally different? And so we can get at that by extracting fibres and then measuring the force and getting the specific tension or the specific force or the specific fibre power of these muscles. This shows a histochemical stain from my PhD work where we're able to take muscle biopsies and do slices and then stain it for type 1 fibres. However, a different technique that we're now doing in my laboratory is to take muscle fibres and then, and this is one of my students who's taking the muscle biopsy here of the vastus lateralis, we extract the fibres and then we extract the single fibres themselves. I don't, he does. And then we can take these fibres and we can measure the contractile properties on very small force transducers, and we're doing this work in conjunction and in collaboration with Robert Fitz, who is a very famous muscle physiologist and just happens to be in the building next door to me. And so we've learned this technique and it's quite wonderful. And so we can answer this question, are there sex differences in the specific tension of fibres? We're doing this on young people, both men and women. We're also doing on old adults before and after training. But what I'm going to show you is some data from just the young people. So, and this, before I do though, I just want to acknowledge that one of our collaborators, Scott Trappy, who you may know, has looked at this question before in young and old people, men and women. And what we have here is the myosin heavy chain type 1 fibres and the myosin heavy chain type 2 fibres. And on the y-axis is the peak tension as a function of the diameter of the fibre. So it's sort of like a a way at getting at specific tension. And so if this relationship is linear, you would expect that there's no difference in the specific tension of the fibres. And what he concluded back in 2003 is that while men tend to have a larger and more powerful fibre than the women and all types, there is also no specific tension, the specific tension and the power doesn't really differ between the sexes of each of these single fibres. We're doing the same, but we're going a little bit further, and we're putting these fibres under different fatigue conditions to see if, even though we might have similar specific tension under control conditions, when we take the fibre out and we put them under control conditions of a pH of 7.0 and a phosphate of 4. On the y-axis here you can see we have fibre force, but it's specific to the cross-sectional area of the fibre. And when we put these fibres under different conditions, fatigue conditions, and here we have a very fatiguing condition, you can see that there's actually no difference in the way that those specific fibres actually respond to fatigue mimicking environments. So it's not due to the differences, or at least our preliminary evidence. This represents 3 males and 2 females, although we've got 34 fibres, and I've combined the myosin heavy chain type 1 and type 2 here. It doesn't seem to be that there's fundamental differences in the way fibres of males and females behave. So I've been talking about maximal contractions. I'm going to briefly just show you a set of experiments on submaximal contractions. I was really interested in this area because, as I said, we know that the sex difference in fatigability is very specific to the task. And the other unique thing is that the ability to drive the muscle during a maximal task may not represent the limitations in activation during submaximal tasks. And so we can measure maximal force, but it may not be really telling us what's going on during the submaximal task. And Roger Anoka was even brave enough to say it's likely that limitations in activities of daily living maybe are more related to activation issues rather than the capacity of the muscle to develop force or power. So because I was really interested in this area, we came up with this, I don't know if it's unique, but this study design where we asked a group of young men and women to perform a sustained contraction at 20% of their maximum under control conditions. We got their rating of perceived exertion, we measured blood pressure, heart rate, EMG, the whole lot. But then we got them in another condition. We asked them to count backwards by 13s from a 4-digit number. Very difficult task, I find. And we would change it up all the time. I won't do it in front of my subjects, or in front of my students, that's for sure. And what we found, this task increases anxiety, it also increases mental attentiveness. And so here we have the results. So on the y-axis here is the time to failure under controlled conditions, which is what we'd expect. We'd expect the women to be able to sustain the contraction longer than men. And here we have when the men and the women were under this cognitive demand task where they were counting backwards by 13s from a 4-digit number, and they were performing the task itself. And you can see the women had a much greater decline in the time to failure than the men. And so we started to look into this, and we're interested to see if it's just mental attentiveness, if it's just the fact that they were being distracted. So we performed the same experiment on many of the same subjects, but this time, rather than counting backwards by 13s, we got them to count backwards by 1. So it's the same mental process, but it's a very easy task. And we found that there was no difference for the women or the men. So and we've shown this in a bunch of studies now, and in some older adults as well. Now, interestingly, in that first study, what we showed that the cardiovascular response was very different for the women during the cognitive stressor or cognitive demand task. This is a little bit complex, but we've got mean arterial pressure, heart rate, and rate pressure product, and so this is the product of these two here. But you can see for mean arterial pressure, for instance, these are the young women under control conditions, and this is during the cognitive stressor task. So they've got an increase in blood pressure as well as heart rate, and certainly their rate pressure product increased as well. The men had small changes, but certainly nowhere near to the extent of the women. And so interestingly, for the same task, but just merely imposing a cognitive demand task, the cardiovascular response was quite different. We're really interested we also measured EMG and rating of perceived exertion, and we actually found, on average, we find no differences between the two tasks, which surprised me. I thought we'd find much greater rates of perceived exertion during the cognitive demand task. In fact, we found in this study, we found a slight reduction, which I can't really explain. What we went on to study was whether their supraspinal fatigue differed at all at the end of the task, but remember, this is during maximal contractions, so which may not be that relevant to what's going on during the submaximal task. And here we have the superimposed twitch force, which increased for the stressor condition and the control condition for both men and women. It wasn't different, and it was identical at the end of the task. This here shows the maximal voluntary contraction force, which was identical for the men and the women after each of the tasks. So we're at a bit of an impasse where we're trying to understand exactly what's going on. And the only thing that we've been able to parcel out so far is that this difference in the time to failure between the control contraction and the cognitive demand task is related to the strength of the individual. And so this is obviously something secondary, and there's a lot more studies to be done in this area. And is it merely just a product of how long the women are going? And we've tried to address that by strength matching men and women so that they go the same amount of time. That's very difficult to do, to find strength matched men and women for the elbow flexor muscles. We've also done we've done the lower limb, we've done the tibialis anterior, and found no effect there. So it's very specific to the elbow flexor muscles, although that's the only other muscle that we've tested besides the tibialis anterior. So that was just to give you a bit of taste of some of how the sex difference can really change during submaximal tasks. I want to briefly go on to dynamic tasks, and there's a lot yet to be done here. But is this relevant? Is this model really relevant? And are there any sex differences in fatigability during dynamic tasks? And the story is really mixed. It's not clear at all. And that sort of makes sense to me. There's so many variables. There's speed as well as contraction intensity. So there's different dimensions here that are even more complex than the isometric. But on the y-axis here, we have the sex differences in fatigability as a function of contraction intensity. And you can see that there's no really clear response here. And here we've got lengthening contractions, where it may even suggest that there's even greater fatigability, although we've just published a study in European Journal of Applied Physiology where there was no difference at all in the knee extensor muscles. So it's not clear here. But one thing I think is that I can pull out from this is possibly the speed of contraction may affect the sex difference. And what we've got here is we've got one of the first studies we did in this, published 2 years ago. We asked subjects to perform elbow flexor muscle contractions at about 60 degrees per second. They were lifting and lowering a load. And what we have here is young people and old people, and we found again that the women were able to sustain the contraction longer, or the task longer than the males, although the sex difference isn't quite as large as what we see during isometric contractions, although it is in the old adults. But what we found is that it was contractile mechanisms that explained this sex difference in the task failure for both the young and the old adults. Here we have the superimposed twitch force during control contractions, at task failure, and then also 1 minute after. You can see there's absolutely no difference in their supraspinal fatigue, which is in contrast to what we saw for the knee extensor muscles during the maximal sustained, during recovery from the maximal sustained isometric contraction. In fact, most of the results were explained by these peak rates of relaxation, where men had a faster relaxing muscle than the women prior to the task. When you take it as a percent of their control contractions, you can see that the men had much greater decrements in the speed of the muscle compared with the women. And so again, like I said, contractile mechanisms explain the sex difference. We then asked, in a separate study, we asked a group of men and women to perform contractions as fast as they could. Again, we loaded them up at 20% of their maximum. And this is what it looked like. We asked them, so here we're controlling for speed, and they've got a constant load. And again, it's the elbow flexor muscles, but these are maximal velocity contractions given a 20% load. And this is what we found. We found absolutely no sex differences in the reduction in power or the reduction in the MVC that occurred during and after the contractions. And you can see here we've got the men and the women at the beginning and the end of each of those 30 contractions, and there's absolutely no sex difference there. And so when you put all those studies together, this on the y-axis here is the sex difference in fatigability for the isometric contractions when they're performing contractions at 60 degrees per second and during maximal velocity. Well, that's not really maximal velocity, it's maximal velocity given a 20% load. You can see there's this massive reduction in the sex difference. So it's really dependent on the velocity of the contraction, at least for the elbow flexor muscles. And so again, it shows that the strength of the contributing mechanism to the sex difference will alter with the details of the task, which includes the muscle group involved, as well as whether it's dynamic, the velocity of the task, and submaximal. Okay, so what I've shown you so far is that the sex difference in fatigability can be very task dependent, that the contractile mechanisms can be primarily responsible for the greater fatigability of men compared with women for control and perfused conditions, at least for the upper limb. And that, last of all, that the neural mechanisms stimulating the central nervous system during maximal efforts can show greater decrements in voluntary activation for men compared with women for some of the lower limb muscles, but imposing cognitive demand during a sustained fatiguing contraction can really increase the fatigability in women more than men. So in the last, this won't take too long, but I think this is probably the most interesting part of the talk. I think it's fascinating. I want to convince you that the numbers of men and women that we study really does matter. And this came out of some data where we were looking retrospectively at world records, but also records of elite runners. And I sort of fell into this area when a journalist called me up and after the Beijing Olympics said to me, is there a sex difference in the age of marathon runners? Because if you remember the Beijing Olympics, the marathon, the guy who won the marathon was 21 years of age and the woman was, I think she was 38 years of age. And I said, I have no idea if age matters. But I said, I can find out. So we went back retrospectively and looked at the age of these marathon runners. And we found no difference at all in the age that men and women primarily win these marathon performances, these events. It's about 29 years of age. But out of that, I said, well, we're not going to waste all this data. We're going to look at their performance as well. And that's what came out of this. And this was a subset of the data that we then published in 2013. And so what we have here is I'm suggesting that the participation ratios of males and females within an event and within a group will predict the sex difference in marathon performance. So let me just walk you through this. So what we've got here is the first place finishers in the New York Marathon. And with this data set, we're able to get 10-year age brackets, and we're able to find the number of men and women within each age bracket, and we're able to find their performance. And then we're able to get the sex difference in performance, and then plot it as a function of the ratio of the men to the women. So on the y-axis here, we have the sex difference in speed of all the first place finishers across different age groups up to 70 years of age. And remember, you've got to remember, historically, women weren't allowed to run the marathon until the early 1970s. It was illegal. And the first marathon really wasn't run until 1984 in the Olympics, which I find horrifying, but still, that's where we're at. And so a lot of these older women had never even been able to participate in marathons. And so they probably weren't even primed to even think that this was an option. And so here we have this variability in the numbers of men and women performing across age groups. And that contributes to this. And so here what we have is we get this linear relationship that the sex difference is larger when there's less women relative to men within an age group. So this data point here represents that there's about 24 men to 1 female in that age group. Okay? So on average, if you take all this data, it's about a 16% difference, sex difference. Now remember, the world record is about 10%. And I actually argue in a paper later it should be about 12%, but that's another story. But it's about 16%. So if we can say that 2/3 of this data, 11%, 10%, 11% of this 16% is due to physiology, then what's the other 5%? And I'm suggesting here that the other third is participation. And in fact, when you get a ratio of 1:1, which occurred in the 20 to 24-year-olds, the sex difference happens to be about 11%, which is what you'd predict. So I thought this was great. This can give us a bigger window into understanding what if we are not including women in our exercise performance studies at the same rate that we're including men. Maybe we truly don't understand the physiological sex differences that are there. And so I went back to the fatigability studies that had been conducted. I went back to 3 major reviews and looked and just went through the references, and then got my research assistant to go and count the number of men and women in each study. And that's all we did. We took 200 studies, and this is what we found. So, and between 1973 and 2015, and on average, there was just about almost 2,500 men represented in those studies, and about half of that was women. Now, this represents the studies that included both men and women. You'd expect them to be the same or almost the same, if they were equal in number. But you can see there's a lot more men involved in understanding the physiological differences in fatigability. And in fact, have we improved over the years? Well, we have. We've improved in inclusion of women. So on the y-axis here is the women to men ratio. So by 2015, for every male included in a fatigue study, you had half a woman. That's what that says anyway. But I want to suggest to you that the disproportionate testing of men and women and the underreporting of sex effects, which does occur when both men and women are included, can really mask an understanding of the sex differences in fatigability and exercise performance. And now I just want to finish with new opportunities, and this will be brief. I want to give you ideas, because do we just throw our hands up and say men are always going to be studied? You know, is there always going to be this sex bias? And I've got some suggestions, because it's not always easy to include women, and I understand that. And there's lots of barriers to it, because what do you do with the menstrual cycle? That's the most common question I get. What do you do with that? It's easier just to test men. Well, first, one thing that you can do is reanalyze existing data for possible sex differences if you have included women and just haven't reported it. And this is an example of a study that we did. Well, I was doing my PhD, and it was one of my colleagues, and we only published the data last year. But the study was originally about exercise training in type 1 diabetes. And we took muscle biopsies, and we did a whole host of things, and we trained them and then looked at the calcium ATPase activity in the sarcoplasmic reticulum after training. And that was the original intent of the study. She happened to include both men and women. And I said to her, why don't you look at whether there's sex differences in the calcium ATPase activity? Because that could actually be, I bet there's big sex differences there, and it's just never really been done before. And so that's what she did. And we found, so what we said is that although not part of our original hypothesis, after examination of the results from this study, we also compared both men and women, basically. And this is what we found. We found that basically the sex difference was much greater than the training difference. And this got published in Journal of Applied Physiology, and I think it got into that journal because of those sex differences that we saw, because it was fairly novel. A second thing I want to suggest to you is that we do single-sex studies. A lot come from here, some have come from me. I've done just men, I've done just women. So what do we do with that? Well, I'm an editor of the Medicine, Science, Sports and Exercise, and I encourage all people who contribute their papers to, and I'm editing, that they indicate the sex of the cohort in the title and the abstract. So if you do just men, don't ever assume that it also is relevant to women. My actual hope is that it would be, and it probably is, but we can't assume that until we test it. So let's just declare it in the abstracts and in the titles. The last thing I would suggest is that in future studies that we include women. It's not that difficult, and test enough men and women to determine if sex differences exist or not. In each of the studies in my lab, that's what we do. Yeah, it's extra work, but I think it's really, really worthwhile. And so I'm just going to suggest what we can do to go forward. We can look at we can see this as a new opportunity rather than a burden. And a new opportunity to see, well, wow, maybe there are sex differences that we never even dreamed of or never even thought of before. And like I said, a lot of people say to me, well, what do we do with the menstrual cycle? Well, I say you record it, that's all, and you test, because women have to perform no matter what part of their menstrual cycle they're in. And also, all the studies we've done, we've found no difference across the menstrual cycle in fatigability or contractile properties. In fact, there was a poster yesterday saying the very same thing. And if there are differences, I would suggest they're probably minor, and the fluctuations in performance across the menstrual cycle are probably very small relative to the differences between men and women. So just go ahead and test them and just record where they are in their menstrual cycle, women. There's also studies to be done on hormone replacement therapy. I'm also suggesting that we can go forward with clinical populations and asking the questions, do sex differences exist in fatigability in these clinical populations, and also with athletes and injury and rehabilitation. And I think I am going to end there. So just to summarise, what we know so far is that the sex difference in fatigability and the mechanisms are really specific to the demands of the task, that numbers matter, and that by increasing the numbers of women in fatigability studies will aid in our understanding the true physiological differences, and that there's lots of new opportunities to move forward by including women. And I certainly need to thank all the sponsors. I thank ACAPS and ROMU for inviting me. I've had a fantastic time. And this is my laboratory here. I want to point out Vianney Rosend, who's been a fabulous host to me, and he was with me for a year. I just want to tell you a story. He first came to the lab for 10 days, and I said to him, and he said, well, I said, you know, I'd love to have you for 3 years. And he said, well, I can only come for 1. And I said, no, 3 or none. And so we were both a bit dejected because I had this large grant that I needed to hire someone on. And then after about 10 days, I thought, you know, I went to the Gandivia lab and did 2 studies in 6 weeks. I'm going to tell this guy that he's got a year and he better work really hard. So he came to my lab and for a year and just worked his tail off. And he was fantastic. And so that's my French connection with Dijon at the moment, although he's not in Dijon now. But so I just really want to acknowledge him and his efforts in my lab, and he presented some of the data yesterday. So thank you very much.
Thank you, Sandra, for this great talk. So we have time for 1 or 2 questions. Yes.
Thank you for this presentation. I have a question. If you have analyzed or showed some differences about antagonist implication during the fatigue task or during the dynamic task, that's very different between the methods that are involved in the task. So do you have any...
So you're asking about are there sex differences in antagonist activation? We usually, in the past, we have normally looked at that and we have found no differences for the elbow flexor muscles. We found it harder to do that with the knee extensor muscles, but certainly for the elbow flexor muscles, there wasn't any difference in the activation. It's a good question. Can you say that again? Is it a difference in?
Sedentary men versus women and trained men versus women?
I don't think so. I think, so the question was, is there a difference between sedentary and active men and women? On average, at least in the US and in Australia, women tend to be more sedentary than males, at least self-report. And so that may factor in, but we do measure physical activity in all our studies, so we try and control for that. So the question really is, does physical activity make a difference to fatigability? And it certainly can, but we try and control for that with our studies.
I can speak loud.
Thank you.
You had a difference in cortical voluntary activation, I think, in the knee extensors. And could it be that actually, because there is a large heterogeneity in the motor units, difference between male and women, so maybe the men have more large motor units. Could it be simply that the cortical drive is actually identical between men and women, but simply because the men have larger motor units, it's harder to activate, and that's why you have this difference in corticospinal activation. So maybe there is no cortical difference, it's just a motor unit difference, and maybe with CMF and stuff like this, you could check all that.
Yeah, that would mean that the range of... So we don't know if there's a difference. So there's different ways to answer that question. We don't know if there's a difference in the number of motor units. But the fibres within those motor units are bigger in the males. And so that then leads to these difference in the type 1 area. I should have been more clear about that. We don't know if there's, and I wouldn't imagine why there would be. So that is a possibility if that be the case, but I don't think the physiology is that different between the males and the females.
One more questions? Maybe? Sam?
Go on, Sam. I was waiting for a question from you.
Actually, just a consideration, because you mentioned that, because we also found the RPE wasn't different in a dual
that
task.
surprised me. Yeah.
In a dual task consideration. And actually it has to be expected. Because when you ask RPE, you ask how do you feel right now, and when people do it, they pay attention to the scale and not doing the cognitive task. So you're asking them to rate and no more a dual task thing. And actually, from behavioral economics, we know that actually if you're exerting more effort than in the control condition, before you ask the RPE, they think the contrast in effort, because so you remove the second task, is bigger, and that people tend to be biased and give you actually less rating.
Right.
Yeah. So my suggestion that we use successfully in our study also with the ROM1 is to use, for example, the NASA scale, which is a retrospect. So after the task, they retrospectively give you a rating of mental demands, physical demands, effort.
That's a great idea.
And that shows differences between tasks that have, dual tasks or different.
I want to talk to you about it.
Yeah.
That's great. Thank you.
Okay, thank you. We have to stop now. Thank you again, Sandra.